And let me change to full screen. Okay, let me change to full screen. My computer is a bit slow. Okay, so last video I did 2.6. We studied about void functions, parameters, local scope, and let's start with 2.7. Okay, take a look at this seemingly innocent sample program. So include IOStream, sum of 3 and 4 is add 3, 4. Then the addition is done here. Okay, you would expect this program to produce the result. The sum of 3 and 4 is 7. But in fact, it doesn't compile at all. Visual Studio produces the following compile error: add identifier not found. The reason this program doesn't compile is because the compiler compiles the content of the code file sequentially. When the compiler reaches the function called add on line 5 of main, it doesn't know what add is because we haven't defined add until line 9. That produces an error, identifier not found. Um, when addressing compilation errors or warnings in your programs, resolve the first issue listed and then compile again. To fix this problem, we need to address the fact that the compiler doesn't know what add is. There are two common ways to address the issue. Reorder the function definitions. So add up here, and then main comes later. This option is not always possible. Let's say we are writing a program that has two functions A and B. If function A calls function B and function B calls function A, then there is no way to order the functions in a way that will make the compiler happy. If you define A first, the compiler will complain it doesn't know what B is. Okay. Use a forward declaration. We can also fix this by using a forward declaration. A forward declaration allows us to tell the compiler about the existence of an identifier before actually defining the identifier. Okay, so we declared add here and then we defined it here. This allows us to tell the compiler about the existence of a function before we define the function's body. This way, when the compiler encounters a call to the function, it will understand that we are making a function call and we can check to ensure we are calling the function correctly. To write a forward declaration for a function, we use a function declaration statement, also called a function prototype. Function declaration consists of function's return type, name, and parameters type terminated with a semicolon. Okay, let's see. So Okay, I understand. Keep the parameter's name in your function declarations. It is worth noting that function declarations do not need to specify the names of the parameters, as they are not considered to be part of the function declaration. Okay, this I didn't know. In the above code, you can also forward declare your function like this. However, we prefer to name our parameters. This allows us to understand what the function parameters are just by looking at the declaration. You might be wondering why we use a forward declaration if we could just reorder the functions to make our programs work. I mean, didn't they address the second issue? The function A and B stuff. Most often, forward declarations are used to tell the compiler about the existence of some functions that has been defined in a different code file. Reordering isn't possible in this scenario because the caller and callee are in completely different files. We will discuss this in more detail in the next lesson. So the next lesson is about multiple files. Forward declaration can also be used to define our functions in an order agnostic manner. This allows us to define functions in whatever order maximizes organization by clustering related functions together or reader understanding. Less often, there are times when we have two functions that call each other. Reordering isn't possible in this case either. That's the case they were talking about. New programmers often wonder what happens if they forward declare a function but do not define it. The answer is it depends. If a forward declaration is made but the function is never called, the program will compile and run fine. However, if a forward declaration is made and the function is called but the programmer never defines a function, the program will compile okay, but the linker will complain that it can't resolve the function call. Also, there's a linking error. Let's test this. So let's copy and paste it here, and it's not responding. Declaration versus definition. Forward declarations are most often used with functions. However, forward declarations can also be used with other identifiers in C++, such as variables and types. They have a different syntax. Okay, declaration and definition. A declaration tells the compiler about the existence of an identifier and its associated type information. This is a declaration and this is a declaration. A definition is a declaration that actually implements or instantiates the identifier. So this, wait, hold on. Tells the compiler about the integer variable named x. In C++, all definitions are declarations. Therefore, int x is both a definition and a declaration. So how is it possible to declare a variable without defining it? How is this instantiated? If it has a garbage value, then we still call it instantiated, right? The default instantiation. Declarations that aren't definitions are called pure declarations. In common language, the term declaration is typically used to mean a pure declaration. So, okay, the one definition rule. The one definition rule is a well-known rule in C++. It has three parts. Within a file, each function, variable, type, or template in a given scope can only have one definition, Definitions occurring in multiple scopes do not violate this rule. Definitions occurring in different scopes do not violate these rules. Okay, local variables defined inside different functions or functions defined inside different namespaces. Within a program, each function or variable in a given scope can only have one definition. This rule exists because programs can have more than one file. Functions and variables not visible to the linker are excluded from this rule. Types, templates, inline functions, and inline variables are allowed to have duplicate definitions in different files, so long as each definition is identical. You haven't covered most of these things yet, so don't worry about this now. We'll bring it up when it's relevant. Okay, this part, the third part, I don't understand it clearly. This I understand, but I know what namespaces are. Well, I have an idea of it. Violating part 1 of the ORD will cause the compiler to cause a redefinition error. Violating ORD part 2 will cause the linker to issue a redefinition error. Violating ORD will cause unidentified behavior. So let's see. Within a file, each function, variable, type, or template in a given scope can only have one definition. Definitions occurring in different scopes. Okay, so only within one scope there. You can only have one definition per scope. Isn't it required to have a definition? Within a program, each function or a variable in a given scope can only have one definition. Yeah. So in a given scope, you can only have one definition. Within a program, each function or variable in a given scope can only have one definition. Types, templates, inline function, and inline variables are allowed to have duplicate definitions in different files. So this here is a violation of ORD. We have already defined function add int. Okay, because within a file in a given scope can only have one definition. So in a global definition, in a global scope, or maybe in a file scope, there are two definitions here. It is not a violation of ORD part 1 for main to have a local variable defined as int x and add to also have a function parameter defined as int x, because they're in different scopes. I want to see examples of 2 and 3 because I'm getting confused what they mean by within a program. So within a program, like multiple files included. A function prototype is a declaration statement and includes function's name, return type, parameters type, and optionally the parameters name. Function declaration tells the compiler that an identifier exists before it is actually defined. I thought declaration and prototype were the same thing. We use a function declaration statement, also called a function prototype. So declaration and function prototype are the same thing, right? How do we declare a forward declaration for functions? For functions, a function declarator prototype serves as a forward declaration. Write a function declaration for this function. I think just have to write this statement with a semicolon. For each of the following programs, state whether they fail to compile, fail to link, or compile and link successfully. Let's see. So you have add in 3. Okay, this doesn't compile because this doesn't match with the declaration. The compiler will complain that it can't find a matching add function that takes 3 arguments. B. Isn't this the same thing? If the two declarations are different, no, this will still cause a compiler error for the same reason here. The compiler will complain that it can't find a matching add function that takes 3 arguments. The forward declaration add only has 2 parameters, and the definition of function add that has 3 parameters hasn't been seen yet. I think it would be a linking error. Doesn't link, the compiler will match the forward declaration to add the function call to add in main. However, no add function takes 2 parameters was ever implemented. We have only implemented one that took 3 parameters, so the linker will complain. So 3 here, 3 here. Names don't match. I think the parameter names don't matter. Compiles and links successfully. The types in the function calls to add matches the forward declaration, and definition to add also matches. The fact that the names don't match the declaration doesn't matter, as the names of the declaration are optional. So I think this will also compile. Yeah, compile and links. This also compiles and links. Right. These are like two different, right? Two different functions. Two different function declaration. Let me see. Return x plus y. I need to check my stream because it says it is connected. Did we add a semicolon outside the braces? I don't think so, right? Okay, let's run this. Like, I think this would work. And so why is my chat not loading? Yeah, 12 and 7 to compile correctly. Well, it works. Okay, wait, let me check my YouTube. It seems to be working fine. It seems to be working fine. Okay, let's run this. Like, I think this. Okay, let me change the first screen again. Programs with multiple code files. Adding files to your project. As programs get larger, it is common to split them into multiple files or for organizational and reusability purposes. One advantage of working with an IDE is that they make working with multiple files much easier. You already know how to create and compile single file projects. Adding new files to existing projects is very easy. In Visual Studio, right click on the source file folder or the project name in the Solution Explorer video, then add new item, right? And then the C++ file. Let's see. So this is my project. Add new item. I will call this second.cpp. Okay, we have a new file. And then what? Keep going down. Because the compiler compiles each code file individually and then forgets what it has seen, each code file that uses stdcout or stdcin needs to include iostream. In the above example, if add.cpp has used stdcout or stdcin, it would have needed include iostream. When an identifier used in an expression, the identifier must be connected to its definition. If the compiler has seen neither forward declaration nor a definition for the identifier in the file being complained, it will error at the point where the identifier is used. If a definition exists in the same file, the compiler will connect the use of the identifier to its definition. We have no clue what's happening. Okay, multi-file example. So we include iostream. We have this add function and the add declaration and definition here. When the compiler reaches the function call to add on line 5 of main, it doesn't know what add is because we haven't defined add until line 9. Our solution to this was either reorder the function, placing add first, or use forward declaration for add. Now let's take a look at a similar multi-file program. So add here, add here. A compiler may compile either add CPP or main CPP first. Either way, main CPP will fail to compile, giving the same compiler error as the previous example. Wait, if main CPP compiles first, no. If add.cpp compiles first, and then main.cpp compiles second. Wait, does it forget the previous file? The compiler compiles each file individually. It does not know about the contents of other code files or remember anything it has seen from previously compiled code files. So even though the compiler may have seen the definition of function add previously, if it compiled add.cpp first, it doesn't remember. This limited visibility and short memory is intentional for a few reasons. It allows the source code of a project to be compiled in any order. When we change a source file, only the source file needs to be recompiled. It reduces the possibility of naming conflicts between identifiers in different files. Our option for a solution here is are the same as before. Place the definition of function add before function main to satisfy the compiler with a forward declaration. In this case, because function add is in another file, the reordering option is impossible. The solution here is to use a forward declaration. So this stays the same. They declared it here. Now when the compiler is compiling main.cpp, it will know what identifier add is and be satisfied. The linker will connect the function call to add in main.cpp to the definition of the function add in add.cpp. Using this method, we can give files access to functions that live in another file. Can we import it the same way we do with include? If we have declaration of add in another file. When an identifier is used in an expression, the identifier must be connected to its definition. If the compiler has seen neither a forward declaration or definition for the identifier in the file being compiled, it will error at a point where the identifier is used. So what they're saying is, or here it reaches add, but there was no declaration, then it will cause an error. If the definition exists in the same file, the compiler will connect the use of the identifier to its definition. If the definition exists in a different file, the linker will connect the use of the identifier to its definition. Otherwise, the linker will issue an error indicated that it couldn't find a definition for the identifier. There are plenty of things that can go wrong the first time you try to work with multiple files. If you tried the above example and ran into an error, check the following. Get a compile error about add not being defined in main. You probably forgot the forward declaration for function add. If you get a linker error about add not being defined, most likely the reason is that add.cpp is not added to your project correctly. Or B, it's possible that you added add.cpp to the wrong project. When you compile, you should see the compiler list both the main.cpp and add.cpp. Let's go here. Let's see this. And let's declare it as well. So one declaration here, another declaration here. Let's just do int. What font size is this? Is this 11? Yeah. So let it build. First.cpp, second.cpp. How do I know? Like, is there a way to check when the compiler finishes and when the linker finishes? To see, it's possible that the file is set to not compile or link. Check the file properties and ensure the file is configured to be linked or compiled. In Visual Studio, there is an exclude from build option that should be set to no or left blank. Make sure you check each build configuration separately. How do you do exclude from build? Uh, Build, I don't know. It's quiz time. Split the following program into two files, main and input. Okay, so this would just go into the other file. And then this would be declared on top. Yeah, input CPP, and then main CPP with the declaration. Okay, 2.9. Naming collisions and an introduction to namespaces. C++ requires that all identifiers to be non-ambiguous. If two identical identifiers are introduced into the same program in a way that the compiler or linker can't tell them apart, the compiler or linker will produce an error. This error is generally referred to as a naming collision or naming conflict. If the colliding identifiers are introduced into the same file, the result will be a compiler error. Okay. If two identical identifiers are introduced into the same program. Okay, an example of naming collision. So a.cpp, we have myfunc. Then main.cpp, we also have myfunc. When the compiler compiles this program, it will compile a.cpp and main.cpp independently, and each file will compile with no problems. Okay, I think the problem will be with the linker. However, when the linker executes, it will link all the definitions in a.cpp and main.cpp together and discover a conflicting definitions for function myfunc. The linker will then abort with an error. Note that this error occurs even though myfunc is never called. Most naming collisions occur in two cases. Two or more identically named functions or global variables are introduced into separate files belonging to the same program. And the second case is two or more identically named functions are introduced into the same file. This will result in a compiler error. Wait, two or more identically named functions are introduced into separate files belonging to the same program. So this here is an example of a linker error because the compiler won't catch it. And I think if myfunc is defined twice, I think it's like if I define it here and then I define it here twice, this would be a compiler error. Let's see. Yeah, error already has a body. How do I know if it's like a compiler or a linker error? So error 3 5. What is 5 here? Is it the column? Yeah, line 3, character 5. Okay, so we have this, and then there should also be a linker error. It starts with a C, then it's a compiler error. Also, I need to check my stream again because it says it is connected. Okay, I don't see any issue. Yeah, I just have to assume that it works properly. Third time it's doing this. A namespace provides another type of scope region called namespace scope. that allows you to declare names inside of it for the purpose of disambiguity. Any names inside the namespace won't be mistaken for identical names in other scopes. A name declared in a scope region won't be mistaken for an identical name declared in another scope. Only declarations and definitions can appear in the scope of a namespace, not executable statements. However, a function can be defined inside a namespace, and that function can contain executable statements. Okay, I need to see some examples. In C++, any name that is not defined inside a class, function, or namespace is considered to be part of an implicitly defined namespace called the global namespace. In an example at the top of the lesson, functions main and both versions of myfunc are defined inside the global namespace. The naming collision encountered in the example happens because both versions of myfunc end up inside the global namespace, which violates the rule that all names in the scope region must be unique. So imports the declaration of stdcout into the global scope. All the following statements are part of the global namespace. So, okay, compiles but strongly discouraged. So this is okay. This is discouraged. And this is compiles but strongly discouraged. So non-constant global variable definition. Same thing here. And then compiler error executable statements are not allowed in namespaces, but they're allowed in function definitions. The std namespace. When C++ was originally designed, all of the identifiers in the C++ standard library were available to be used without the std prefix. They were part of the global namespace. However, this meant any identifier in the standard library could potentially conflict with any name you picked for your own identifier, also defined in the global namespace. Code that was once working might suddenly have a naming conflict when you introduced a different part of the standard library. Or worse, code that compiled under one version might not compile under the next version of C++, as new identifiers introduced into the standard library could have a naming conflict. It turns out that stdcout's name isn't really stdcout. It's actually just cout, and std is the name of the namespace. Yeah, but I think they should give examples. Explicit namespace qualifier, std. The most straightforward way to tell the compiler that we want to use cout from the std namespace is by explicitly using the std prefix. For example, stdcout. When we say cout, we mean cout defined in the std namespace. The colon symbol is an operator called scope resolution operator. Use explicit namespace prefixes to access identifier defined in the namespace. So, using namespace std, this is a using directive that allows us to access names in the std namespace with no namespace prefix. A using directive allows us to access the names in a namespace without using a namespace prefix. When the compiler goes to determine what identifier cout is, it will match with stdcout because of the using directive is accessible as just cout. Many text tutorial, even some IDEs recommend or use using directive at the top of the program. However, used in this way, this is a bad practice and highly discouraged. Consider the following program. So using namespace std and scout defines our own cout function in the global namespace, and then this will cause a compile error because cout could refer to this, or it could refer to the cout inside the library. Avoid using directives at the top of your program or in header files. They should have given examples of the namespace, like custom namespace. In C++, curly braces are often used to delineate a scope region that is nested within another scope region. Braces are also often used for some non-scope related purposes such as list initialization. For example, a function defined inside the global scope region uses curly braces to separate the scope region of the function from the global scope. So foo is defined in the global scope. Braces used to delineate nested scope for regions for function foo. So within braces is a separate scope. This is different here. X is defined within the scope of main. As X goes out of scope here. Okay, so braces define the level of scope. So that means, okay, if I have my own braces like this, int x 5, this y 6. So these two have their own scope, right? This brace is its own separate scope. And then as soon as it reaches here, it gets deleted, right? So if I do std cout x, and let's see. Yeah, undeclared identifier. Let's remove this. Let's rename the file to math.cpp. And then let's just do this. Okay. They're introducing preprocessors, but how do you declare your own namespace? That's what I want to know. The include and function definitions for and main exist in the global scope region. So they are not indented. I mean, you don't need to indent them. That's just style convention. Okay. It didn't open. Introduction to preprocessors. It's not even opening. Imagine it opens like 3 tabs. When you compile your project, you might expect the compiler compiles each code file exactly as you have written it. This actually isn't the case. Instead, prior to compilation, each code file goes through a preprocessing phase. In this phase, a program called the preprocessor makes various changes to the text of the code file. Historically, the preprocessor was a separate program from the compiler, but in modern compilers, the preprocessor may be built right into the compiler itself. Most of what the preprocessor does is fairly uninteresting. For example, it strips out comments and ensures each code file ends in a new line. However, the preprocessor does have one very important role. It is what processes the include directives. When the preprocessor has finished processing a code file, the result is called a translation unit. This translation unit is what is then compiled by the compiler. The entire process of processing, compiling, and linking is called translation. So basically, that's like converting your project into exe, I'm guessing. So wait, when the preprocessor does its stuff, the source code changes into a translation unit, right? And then when the entire compiling finishes, you get an object file. And then after the linker finishes, you get an exe. When the preprocessor runs, it scans through the code file from top to bottom looking for preprocessor directives. Preprocessor directives, often just called directives, are instructions that start with a hash symbol and end with a new line, not a semicolon. These directives tells the preprocessor to perform certain text manipulation tasks. Note that preprocessor does not understand C++ language. Instead, the directives have their own syntax, which in some cases resembles C++ syntax, but in other cases not so much. The final output of the preprocessor contains no directives. Only the output of the processed directive is passed to the compiler. Using directives are not preprocessor directives. So while the term directive usually means preprocessor directive, this is not always the case. I mean, this can be confusing. So hash include, you have already seen hash include directive as action. The included contents are then pre-processed. Then the rest of the file is pre-processed. When you include a file, the preprocessor replaces the include directives with the contents of the included file. So wait, if we do this twice, like this over here, and then this again over here, does this include the contents of this tree of the file twice? Wouldn't that make the code slow? Okay, never mind. When the preprocessor runs on this program, the preprocessor will replace include IOStream with the contents of the file named IOStream, and then processes the included contents and the rest of the file. Since include is almost exclusively used to include header files, we will discuss include in more detail. Each translation unit typically consists of a single code file, all header files it includes. Macro defines. The define directive can be used to create a macro. In C++, a macro is a rule that defines how input text is converted into replacement output text. There are two basic type of macros: object-like macros and function-like macros. Naming rules as the normal identifiers. This is disconnected and reconnected again. They can use letters, numbers, and underscore. Cannot start with a number and should not start with an underscore. By convention, macro names are typically all uppercase separated by underscores. Okay. When a preprocessor encounters this directive, so over here define main Alex, it replaces my name with Alex, right? An association is made between the macro identifier and substitution text. All further occurrences of macro identifier replaced by this is disconnected again. And text. I don't know why it keeps doing this. I can write something like this is the like fifth time it's doing this. Can do something like random text hello. Then I can write this over here. Can I do that? Can I like write the entire statement? No, I don't think so. I can do this stdc out. Let's see how well this works. So the preprocessor will work first. They will work with all the define statement and replace this text with this text. Yeah. So you can like prank someone by saying, if I do 4, 7. Oh wait, it can't start with a number. If I do add 3, 4. No, it can't do. I don't think it can do that. Only underscore letters and numbers, right? Letters, numbers, and underscores, and cannot start with a number. Okay. Cout. Okay, so the preprocessor converts the above into the following. Avoid macros with substitution text unless no viable alternatives exist. Object-like macros without substitution text. Macros of this form work like you might expect. Most further occurrences of the identifier is removed and replaced by nothing. This might seem pretty useless, and it is useless for doing text substitution. However, that's not what this form of directive is generally used for. We will discuss the uses of this form in just a moment. Unlike object-like macros with substitution text, macros of this form are generally considered acceptable to use. Okay, so conditional compilation. The conditional compilation preprocessor directives allow you to specify under what condition something will or won't compile. There are quite a few different conditional compilation directives, but we'll cover only a few that are used most often. If define, if not define, and define. The if define preprocessor directive allows the preprocessor to check whether an identifier has been previously defined by define. If so, the code between the if define and matching and define is compiled. If not, the code is ignored. Since print Joe it's defined. Well, there's no substitution text, but it's defined nonetheless. Uh, then this code will get compiled, and this code will not get compiled. So in the final .exe file, this will exist, and this will not exist. The line std job will be compiled. The line std bob will be ignored. If define, and if not define, which is okay. If not define is the opposite of if define. It checks whether if print bob is not defined. Slash define happy ending. Have a good day, and then have a bad day. Happy end. Bad end. So let's see. If define what was that? Let's see. If define this is happy end, and I don't understand the notation of this. And this is a bad end. I'm a little confused with the notation. So the scope doesn't change with the if and end define, right? And if happy end here as well. If not I think the editor is checking whether this is defined or not and doing the syntax highlighting accordingly. They didn't seem to indent it. I think that's the notation here. So that this is in line with the rest of the code. It says have a good day, and then if I comment that out, oh yeah, now the syntax highlighting is changing. Have a bad day. F0. One of the more common use of conditional compilation involves using F0 to exclude a block of code from being compiled as if it were inside a comment block. Don't compile anything starting here until this point. What's the point of this? This provides a convenient way to comment out code that contains multiple lines which can't be commented out using another multi-line comment due to multi-line comment being non-nestable. Don't compile anything here, some multi-line comment here until this point. To temporarily re-enable code that has been wrapped in an F0, you can change F0 to F1. Macro substitution within other preprocessor commands. You may be wondering, given the following code, since we define printjo to be nothing, how come the preprocessor doesn't replace printjo in if define printjo with nothing and exclude the output statement from compilation? In most cases, macro substitution does not occur when a macro identifier is used within another preprocessor command. Oh, I understand. So if the substitution here is 9, normally, right? So this bad end is replaced by have a bad day. But if a macro is used by another preprocessor, the substitution doesn't happen. Okay. That's why we have to write 0 and 1 directly. Can we write variables there? What happens if I int x for, what happens now? Or is it specifically checking for a macro? X local variable is initialized before reference, but not referenced. Wait, what? The following warning is treated as an error. X local variable is initialized, but not referenced. Oh yeah, this is seen as a macro. It's not seen as a variable. We call it a macro, right? Wait, let's see. Yeah, never mind. Directives are resolved before compilation from top to bottom. Consider the following program. Define my name Alex. Even though it looks like define my name Alex is defined inside function foo, the preprocessor doesn't understand C++ concepts like functions. Therefore, this program behaves identically to one where define my name Alex was defined either before or immediately after function foo. So preprocessor or compiler are like two different things, right? But preprocessor is built into the compiler, but compiling and preprocessing are two different things. The following also behaves identically to the prior example. Okay. They did not introduce header files, right? No, that's the next lesson. Okay, next lesson they're going to talk about header files. In lesson 2.8, we discuss how programs can be split across multiple files. Now consider the case where you have 100 files and they each require 100 forward declarations. This simply doesn't scale. C++ code files with the CPP extension are not the only files commonly seen in C++ programs. The other type of file is called a header file. Header files usually have a .h extension, but you will occasionally see them with a HPP extension or no extension at all. Conventionally, header files are used to propagate a bunch of related forward declarations into a code file. Yeah, they should have given an example. Why do we need .hpp? Can't we just use .h? Unless .hpp has different, has like more functions. This program prints hello world to the console using stdc out. However, this program never provided a definition or declaration for stdc out. So how does a compiler know what stdc out is? Well, it's written here, right? Include IOStream. The answer is that stdc out has been forward declared in the IOStream header file. When you include a file, the content of the included file is inserted at that point of inclusion. This provided a useful way to pull in declarations from another file. Now let's go back to the example we were discussing in a previous lesson. When we left off, we had two files, add.cpp and main.cpp, that looked like this. Add x5, okay, and main.cpp is like this. If you're recreating this example from scratch, don't forget to add .cpp to your project so it gets compiled in. Let's write a header file. Right. In this example, we used a forward declaration so that the compiler will know what identifier add is when compiling main.cpp. Let's write a header file to relieve us of this burden. Writing a header file is surprisingly easy, as a header file consists of two parts: a header guard, the action content of the header file. This is discussed in 2.12, which is the next chapter. Adding a header file to the project works analogously to adding a source file. Okay, so let's see if I do this, add new item, header file. Uh, should it be capital H? Math.h. Oh, there's a separate thing for header files. What is this Pragma ones? Let's see. So this here now. So the definitions are included in the header file. Now somehow we need to. I think we can do this. Math.h. Wait, math.h is already used. Can I? Hold on. See program files Windows script. This is a different math.h. This is what I want. Wait, hold on. I think there's a built-in math.h, and I shouldn't be using this. What's the difference between angle bracket and this? It says Windows Kit, then include ucut math.h. If I do IOStream, Visual Studio, yeah. Maybe I should rename this to custom math. I don't know. Give me a name. Hmm. Math funks. Oh, never mind. But how does the compiler know which one I'm using? Video include math. A different math.h. I think if I have two header files in different location, I think it prioritizes the closest one first. Prefer the .h suffix when naming your header files. This is a long-standing convention for C++ header files. So what's the point of .hvp? If a header file is paired with a code file, they should both have the same base name. We really should have a header guard here, but we will omit it for simplicity. We will cover that in the next lesson. When the preprocessor processes add.h line, It copies the content of add.h into the current file at that point. Because our add.h contains a forward declaration for function add, that forward declaration will be copied into main.cpp. The end result is the program that is functionally the same as the one where we manually added to the forward declaration at the top of main.cpp. Okay, so add.cpp, include add.h, include iostream, then iostream, this is the header file, include add.h. So cpp add.h, this compiles into this object file, cpp h, and these three together, they compile in main. And then what was this standard runtime library? Then these two are linked together into main.exe. This iostream contains all the declaration but no but no definitions. All the definitions are, I think, are here. How including definitions in a header file results in a violation of the one definition rule. For now, you should avoid putting functions or variables definitions in header files. Doing so will generally result in a violation of one definition rule in cases where the header file is included into more than one file. I see. So if I do math.h here and include math.h in another file and it has a definition, then it will be defined in both files, right? Add.h, here's a definition, main.cpp and add.cpp both contain add.h, but these 4 lines will be here and in add.cpp as well. That will violate the one definition rule. So main.cpp after pre-processing looks like this from add.h. This will compile just fine. And add.cpp will look like this. This will compile just fine. Finally, the linker will run. The linker will see that there are now 2 definitions for function add. This is a violation of ODR part 2, which states within a given program, a variable or normal function can have only one definition. And now I understand this. Do not put function or variable definitions in your header files. Can we declare twice? I think we can, right? We can declare multiple times. We can have the same declaration multiple times. In C++, it is a best practice for code files to include their paired header file if one exists. This allows the compiler to catch certain kinds of errors at compile time instead of link time. For example, something.h, something.cpp, C++, it is a best practice for code files to include their paired header file. Oh, they mean like this. Math.h. Because something.cpp includes something.h, the compiler will notice that function something has a mismatched return type and gives us a compiler error. Okay. So it will catch any errors we make. Source file should include their paired header files if one exists. Avoid including .cpp files. Although the preprocessor will happily do so, you should not include CPP files. These should be added to your project and compiled. There are a number of reasons for this. Doing so can cause naming conflicts. In a large project, it can be hard to avoid one definition rules. Any change to such a CPP file will cause both the CPP and any other CPP file that includes it to recompile. It is not conventional. Okay, now they talk about angle brackets and double quotes. Troubleshooting. If you get a compiler error indicating that add.h isn't found, make sure the file is really named add.h. Okay, you're probably curious why we use angle brackets for IOStream and double quotes for add.h. It's possible that a header file with this same file name might exist in multiple directories. Our use of angle brackets versus double quotes helps the preprocessor helps give the preprocessor a clue as to where it should look for a header file. When we use angle brackets, we are telling the preprocessor that this is a header file we didn't write ourselves. The preprocessor will search for the header file only in the directories specified by include directories. The include directories are configured as part of your project ID compiler settings and typically default to the directories containing the header files that come with your compiler and or OS. The preprocessor will not search for header files in your project source code directory. When we use double quotes, we are telling the preprocessor that this is a header file that we wrote. The preprocessor will first search the header file in the current directory. If it can't find a matching header there, it will then search the include directories. Okay, let's see. If I do something like this, mat.h, and this will do this. This is from, yeah, then add is not defined because it's from a different directory. Yeah, it's like what I said. They should give a compiler error. Yeah. So h and then h. Another commonly asked question is why does an IOStream have a .h extension? The answer is that iostream.h is a different header file than iostream. To explain, it requires a short history lesson. When C++ was first created, all of the header files in the standard library ended in a .h suffix. These headers included iostream, standard def. Okay. The original versions of cout and cin were declared in iostream.h in a global namespace. Oh, I see. And the language was standardized by the ANSI committee. They decided to move all the names used in the standard library into the std namespace to help avoid naming conflicts with a user defined identifier with user declared identifiers. Okay. So however, this presented a problem. If they moved all the names into the std namespace, none of the old programs would work anymore. Oh, I see. That's why there's a different one. This one uses the std namespace. This one doesn't. Modern C++ now contains 4 sets of header files. So naming convention XXX, identifier placed in namespace, std namespace. So CXXX, std namespace required, global namespace optional. xxx.h global namespace. So identifiers have a global namespace and xxx.h. What's the difference between these two? C compatibility old. Wait, what's the okay? C++ specific. And C compatibility old. Do they have namespaces in C? I can't remember. Use a standard header library header file without the .h extension. User-defined header should still use .h extension. So what about the .hpp file? I want to know what happened to that, including header files from other directories. Another common question involves how to include header files from other directories. One bad way to do this is to include a relative path to the header file you want to include as part of the include line. For example, headers my header, more header, my other header. While this will compile, the downside of this approach is that it requires you to reflect your directory structure in your code. If you ever update your directory structure, your code won't work anymore. A better method is to tell your compiler or IDE that you have a bunch of header files in some other location so that it will look there when it can't find them in the current directory. This can generally be done by setting an include path or search directory in your IDE project settings. I think I'll just use this. Headers may include other headers. It's common that the content of a header file will make use of something that is declared in another header file. When this happens, the header file should include the other header files containing the declaration that it needs. Wait, hold on. Headers may include other headers. It's common that the contents of the header file will make use of something that is declared in another header file. When this happens, the header file should include the other header file containing the declaration that it needs. foo.h uses string view. But if we are importing foo.h, can we use the declarations on string view without including them? Transitive include. I think this is what they're going to talk about. When your source file includes a header file, you will also get any other header files that are included by that header. These additional header files are sometimes called transitive includes, as they're included implicitly rather than explicitly. The contents of these transitive includes are available for use in your code files. However, you should generally not rely on the content of headers that are included transitively unless reference document indicates that those transitive includes are required. The implementation of header files may change over time or be different across different systems. Each file should explicitly include all the header files. I didn't include some header in my program worked anyway. This is most commonly asked questions on this site. The answer is it's likely working because you included some other header which itself included some header. Although your program will compile per the best practice above, you should not rely on this. The order of inclusion for header files. If your header files are written properly and include everything they need, the order of inclusion shouldn't matter. Now consider the following scenario. Let's say header A needs declaration from header B but forgets to include it. In our code file, if we include header B before header A, our code will still compile. This is because the compiler will compile all the declarations from B before it compiles the code from A that depends on those declarations. However, if we include header A first, then the compiler will complain because the code from A will be compiled before the compiler has seen the declarations from B. Okay, so wait a minute. So if I add new item header math2, so if I do math2, right, and then if I do math2, these two will not work, right? Let's see. Yeah, these two will not work, but what is pragma once? If I do include math.h, now this will work, right? Yeah. So what are they saying? Header A needs declaration from header B. Yeah, this works. So math2 needs the declaration from math. Well, I mean, it doesn't need the declaration from math, but still. To maximize the chance of skipping includes that to maximize the chance of missing includes will be flagged by the compiler. Order your includes as follows. The paired header file for this code file .cpp should include add.h, other headers from the same project, third-party library headers, and then standard library header. So header file best practices. Here are a few recommendations. Always include a header cards. This will cover, we will cover this in the next lesson. Do not define variables and functions in headers for now. Give a header file the same name as the source file it's associated with. Each header file should have a specific job and be as independent as possible. Okay. Do not include .cpp files. So now header cards. A program that defines a variable identifier more than once will cause a compile error. This is a definition for variable x. Compile error. This is a duplicate definition. Similarly, programs that define a function more than once will cause a compile error. Alright. And then, while these programs are easy to fix, with header files, it's quite easy to end up in a situation where a definition in a header file gets included more than once. This can happen when a header file includes another header file, which is common. In the upcoming example, we will define some functions inside header files. You generally shouldn't do this. Okay, so square.h, the function is defined here. Wave.h includes square.h, main.cpp. Oh, so this gets inside wave.h. So now when you include both of them, there are two definitions getting included. After resolving all the includes, main.cpp ends up looking like this. Duplicate definitions and a compile error. Each file individually is fine. However, because main.cpp ends up including the contents of square.h twice, we have run into problems. Header guards. The good news is that we can avoid the above problem via a mechanism called a header guard, also called an include guard. Header guards are conditional compilation directives that take the following form. We did this before. When this header is included, the preprocessor will check whether some unique name here has been previously defined in this translation unit. If this is the first time we are including the header, some unique name here will not be defined. Consequently, it defines some unique header, some unique name here, and includes the content of the file. If the header is included again into the same file, so some unique name here will already have been defined for the first time. So this is the way of preventing double definition, right? Even the standard library headers use header guards. If you were to take a look at the IOStream header file from Visual Studio, you would see it define IOStream, define, and oh, so if it's not defined before, then define it. And then next time this won't run. And if I take a look at IOStream, but definitions are discouraged, right? So you're assuming that there won't be any definition in the header file. Oh yeah, they did it over here. So this prevents the code from being included multiple times. After preprocessor resolves all the include directive, the program looks like this. Yeah, so it's first defined here. So square h is not defined. Then it's first defined here. And then the function gets defined. So this goes into the compiler. And then this doesn't go into the compiler. So there's no compiler error. Header guards do not prevent a header from being included once into different code files. Header guards do not prevent a header from being included once into different code files. Note that the goal of the header guard is to prevent a code file from receiving more than one copy of the guarded header. By design, header guards do not prevent a given header file from being included into the separate code files. This can also cause unexpected problems. Consider square h. If not define square h, define it and then undefine. Then square cpp. Then main.cpp square.h. Know that square.h is included from both main.cpp and square.cpp. So this is going to be included twice. But the function, this code will run once, right? This means the content of square.h will be included once in square.cpp and once in main.cpp. Oh yeah, sorry. This will happen once here and then once here. Uh, so square.h, the best way, right? The end result is that both square.cpp and main.cpp get a copy of the definition of get square slides. This program will compile, but the linker will complain about your program having multiple definitions for identifying get square sites. The best way to work around this issue is to simply put the function definition in one of the CPP files so that the header just contains a forward declaration. Okay, so you don't have multiple definitions in different files. It solves the problem. We have generally told you not to include function definitions in your header. So you may be wondering why you should include header guards if they protect you from something you shouldn't do. We have generally told you not to include function definitions in your header, so you may be wondering why you should include header guards if they protect you from something you shouldn't do. There are a few cases we will show you in the future where it's necessary to put a non-function definition in a header file. For example, C++ will let you create your own types. These custom types are typically defined in header files. So the type definitions can be propagated out to the code files that need to use them. Without a header guard, a code file could end up with multiple identical copies of the given type definition, which the compiler will flag as an error. I don't get this. Uh, these custom types are typically defined in the header files, so the type definitions can be propagated out to the code files that need to use them. Yeah, I don't understand what they said there. Modern compilers support a simpler alternative form of header cards using the Pragma preprocessor directive. Pragma once. So why does an IO stream use Pragma once? Maybe because they didn't update it. I don't know. Pragma once serves the same purpose as header cards to avoid a header file from being included multiple times. With traditional header cards, the developer is responsible for guarding the header. With Pragma once, we are just requesting the compiler guard the header. How exactly it does this is implementation specific detail. There is one known case where Pragma once will typically fail. If a header file is copied so that it exists in multiple places on the file system, if somehow both copies of the header file gets included, the header guards will successfully dedupe the identical headers, but Pragma once won't, because the compiler won't realize they're actually identical content. The header file is copied so that it exists in multiple places on the file system. If somehow copies both of the header If somehow both copies of the header gets included, header guards will successfully dedupe the identical headers. Oh, I see what they're asking. Okay, I don't see what they're asking. If I have this, if I put this here, would this import the declaration twice? Once here and another here. I think, hold on, because these are two different files even though the contents are same, right? I want to know what the compiled looks like, the compiled version looks like. I mean the pre-processed version looks like. Um, that's what I think. So Pragma won't defend against this if they're like two different files with the same content. But the header guard can, if I have a header guard like if not define, add func, then define add func. If I have something like this, and if I have the same thing here in math 2, what happens? So I import math, this gets imported. I import math 2, this gets imported. But the header guard, when it compiles, the header guard prevents these declaration, but they include this definition. So if this is mentioned twice, like, so when these two are pre-processed, it will look something like this. It will look like this. And then the declaration only happens once. That's what the header guards do. But what Pragma wants is supposed to prevent is, let me think. What is Pragma 1 supposed to prevent? Yet I need to see their examples. Square edge, square.cpp. I think it's like if it's the same file, include math.h. If I have something like this, and if I have these two, without Pragma once, this will be copied here and here as well. And then if it does include math2, then the declarations that will come out from here will also be over here. So basically, it's going to do these two declarations twice. One from math.h and then other one that has a transitive declaration. So it's going to do something like this. So let's see, include math.h, pragma once. If I run this, it should give an error for double declaration. Or maybe not. Okay, let's say it's defined here. Uh, Good. Add. No, then it causes an error because it's defined here. Wait, let's see. Let me think about this. Would this cause a warning or an error? I don't think being declared twice causes an error. Yeah, it didn't. But the point is, it is declared twice, and Pragma once would uh, prevent that from happening. So when it's compiling, when it's pre-processing, mat.h, Pragma once. So when you do include math.h, include math2, since they're Pragma once, this is only included once. At least that's what I think happens. Uh, okay. Yeah, that actually is what happens. Because Pragma ones are basically like header guards. The Pragma directive was designed for compiler implementers to use for whatever purposes they desire. As such, with pragmas, which pragmas are supported and what meaning those pragmas have is completely implementation specific, with the exception of pragma ones. Do not expect pragma that works on one compiler to be supported by another. Because pragma once is not defined by C++ standard, it is possible that some compilers may not implement it. For this reason, some development houses recommend using traditional header guards. In this tutorial, we will favor header guards as they are the most conventional way to guard headers. Okay. Uh, Maybe is there a way to prevent Visual Studio from automatically adding Pragma ones? Maybe I should be. If that's the convention, then that's what I want to follow. If define math func and then put these here. Func. If this gets included, then there will be two copies of that code, of this code, but it will only occur once. It will only appear once in the compiler. Anyways, I'll just delete this. What's the difference between remove and delete? Okay. Smart.h. How do I set VS Code so that it doesn't automatically include Pragma ones? So add header guards to this header file. Add.h. Add h. Add h. I'll do the next two chapters and then I will end the stream. How to design your first program. Step 1, define. Didn't we already do this? Step 1, define your goal. In order to write a successful program, you will need to define what your goal is. Step 2, define requirements. Requirements is a fancy word for both the constraints that your solution needs to abide by, as well as the capabilities that your program must exhibit. Define your tools, targets, and backup plan. Defining what target architecture and or OS your program will run on. Okay, wait. Hold on, I skipped a bunch. Step 4, break hard problems down to easy problems. Trying to figure out how to do these tasks can be very challenging. In such cases, we often make use of the top-down method. The other way to create a hierarchy of tasks is to do so from the bottom up. In this method, we will start from the list of easy tasks and construct the hierarchy by grouping them.